CIDAI is a key element for the Catalonia AI strategy. Our mission is to demonstrate the advantage and speed up the adoption and of innovate and data exploitation and artificial intelligence technologies, with the mission to promote the Catalan ecosystem to become an international reference for trustworthy AI innovation and adoption, both at enterprise and at social level. We are working in several tasks to increase the adoption of this technology in the territory. One of them are these masterclasses. By the way, in the following weeks, we will publish all masterclasses that we are going to do in 2021. Today, one of the partners of CIDAI, the Barcelona Supercomputing Center, will lead this session, Introduction to Basic Deep Learning Concept. The purpose of this masterclass is to give an overview, but without excessive technicalities, of deep learning techniques. So please let me introduce you Dario García, postdoctoral research in the computer science department at BCC. Please, Dario, the floor is yours.
Thank you very much for the introduction, Marco. So welcome to all the attendees. Today's session will be not so brief introduction to deep learning concepts. All of you have a very wide variety of backgrounds. So the goal of the presentation is to contribute to all of you, regardless of how experienced you are in deep learning. So let me share my screen. How will I get started? Okay, so I will try to avoid the very technical details. Some technical aspects will be reviewed, but essentially we'll try to keep it easy. Also, I will try to focus on practical tips because this is usually in practice what I'm most requested about. So how to actually manage to interact with things when you are with your hands dirty. So let's get started. Okay, so I like to start explaining deep learning with a bit of history because it gives a very good sense of context of how we got here and where we came from. So actually, one of the first contributions to the field of deep learning, which essentially deep learning is just a fancy word to mention artificial neural networks that have a lot of layers. And artificial neural networks were born in the 40s. So this was after the work, the groundbreaking work on brain analysis from Ramón y Cajal and many others. So after the structure of the brain and the structure of neurons, of biological neurons was discovered, some researchers started considering how we could adapt this mechanism to automate it, to synthetic design of neurons and brains. So one of the first contributions was by McCulloch and Pitts in '43, in which they started designing how could these neurons interact with one another. So you can see here on the right different, this is actually from their paper in 1943. This is the designs of neurons they considered, in which there were several neurons connecting to one another. So the output of one neuron is the input of the other. So we can kind of create networks in this way that compute something. So on top of that, Howard Hebb in '49 started what is still known today as the Hebianism approach to learning. And it's essentially the idea that if two neurons that are connected fire at the same time, concurrently, in a coordinated manner, then it means that they should be strongly bounded together. So essentially, this idea is bounding the topology of the network, so which neurons are connected to one another, with how they behave. So if we persist this kind of relationships through, for example, a parameter that specifies every link between two neurons, the strength of it. So this is called, for example, we can call it a weight. So if we implement this kind of relationship between neurons, exemplifying what's the strength of the connection, we can have both learning, because we can modify this weight and make it larger or smaller, depending of if it's convenient or not. And also memory, because once we have this number here written, persisted, we can remember this state and access it later on. So this Hebianism approach is what provides learning and memory, and pretty much all deep learning research is based on both of these ideas. So on top of that, this is very cool. In 1948, Rosenblatt actually built a deep neural network with these ideas. So you can actually see the web of wires that it was. It was quite a mess. It actually had one single layer of artificial neural networks. The other were sensory units or response units. But it was quite impressive at the time. It's quite impressive today still. And Rosenblatt contributed by adding a threshold function. So a threshold function defines when should a neuron fire in response to its inputs. When should it fire an output in response to its inputs? So it either fires with a 1 or it does not fire with a 0. So the strength with it will fire is the weight that we have been learned and a bias that is added, and with that we can implement the behavior of the network. So this was the threshold function, and with that we have a working neural network. And Rosenblatt was expecting this to work very well, and the press was on it, and there was a lot of buzz in society that this was going to be the next big thing, a bit like today, right? Where deep learning and artificial intelligence seems like it's everywhere. So it was the same back in 48, but unfortunately it didn't quite work because there was one very important limitation. That actually Rosenblatt was very well aware of it, and it was that Rosenblatt didn't know, or anybody else at the time didn't know how to train neural networks that had more than one layer. Essentially, if you only have one layer of neurons, one depth, one level of depth, so the input only crosses through one artificial neural network, you cannot learn nonlinearities. So to understand what a linearity or nonlinearity is, this is a very good example. So we have here white examples and black examples. So with one linearity here, with a single line, we can separate the white and black examples. And we can also do the same for this. So this is the AND function, and this is the OR function, these points. But here we have the XOR function, in which we have the white in this diagonal and the black in the other diagonal. And here we cannot separate it with a single line. So this is not linearly separable. To separate this, we would need some kind of curvy line that goes something like this, which cannot be computed with a linear function. For computing this kind of curvy function, we need a nonlinearity. And for computing nonlinearity, we needed more than one layer of neural networks. And Rosenblatt and later Minsky and Papert recognized that this could not be achieved with what was known at the time. So this paper came, actually it's a book. This book came around in '69 saying that, okay, neural networks are cool, but they cannot do nonlinearities, and that's dramatic. And the whole field was abandoned because of that. People overreacted to it. Instead of working on trying to solve it, they kind of abandoned the field in the 80s, in what is known as the first artificial intelligence winter, where funding was cut and researchers were abandoned, and society looked away from AI. They moved from what is known connectionism, that's the idea of neurons with one another, to symbolism, in which we represent knowledge in an abstract manner. So with that, in this kind of point, the people working on doing research on artificial neural networks were relatively few, because the field was pretty much abandoned. But eventually, those who remained found out the solution to the problem, which is, simply put, it's the backpropagation algorithm that specifies how can we train neural networks of several layers. Essentially, it's a version of the derivative chain rule. I'm not going to get mathy here. It's just a manner of how to pass the responsibility of error from the end of the network towards the beginning. So essentially, it's a mathematical mechanism so that regardless of what depth a neural network, a neuron is, we can still attribute what's its contributions to the error, and therefore we can modify it to decrease the error of the overall function. This was discovered actually several times in history. The first recognized one was Wervers in '74, but the most popular one is Rumelhart and Hinton in 1985. So this ended the neural networks winter. After this, after '85, this functionality was recognized and people started using artificial neural networks again, which was great. And on the other hand, we had this second AI winter because expert systems that were the ones that were running at the time didn't quite work as well as it was expected, which is kind of a recurring thing in artificial intelligence. And so funding was cut again for expert systems. So it's just a matter of when is the third winter going to come, which might not be far from now. Okay. So this is a bit of history. Now let's get into a bit more detail of how they actually work today. So essentially, there's a lot of designs of, well, yeah, let's pause here and see if there's some questions or comments. It's a good time to see. I think there's nobody has any question or comment. Okay, so I will move on. So essentially, right now we have a lot of designs of architecture for neural networks. We have neural networks for images. We have neural networks for sequences. We have transformers. We have generative models. But there's a certain amount of things that are pretty much common for all designs, and this is what I will try to detail here. That being said, feed-forward neural networks are considered to be the most simple ones, in which you have simple set of layers that feed forward information from one to another. So this is essentially the most essential design. So how we train a feed-forward neural network through this backpropagation algorithm. So essentially, we have, let's assume the supervised learning example, which is the simplest one to understand. So we have a set of examples for which we know how we want to the network to behave when it sees them. So for example, we have images of cats and images of dogs, and we want that whenever we input an image of cat, the neural network produces a 0, and whenever we put an image of a dog, the neural network produces a 1. So this 0 or 1 is the label, is the expected outcome. And what we want is that the neural network learns a function, learns a transformation of the data that goes from the input image to the output 0 or 1. So this is what is called the forward pass. We are passing the information forward through the network to see what's the actual prediction of the network. And then when we reach the end, the neural network will either provide 0 or 1. In practice, it provides a number that is between 0 and 1 based on the confidence that it has. And then we can compute which is the error that has been computed. Since we know the actual label, so we know that if the input image that we were passing was a cat, so it was expected to provide a 0, but it provided 0.2. So the error it made was 0.2 because it should have given a 0. So now we want to minimize this error. And what we do is the backward pass. So we get this error and we backpropagate it through a network. This is what the backpropagation algorithm does, finding for every single parameter for all those weights associated to the connections between neurons, which is the responsibility of that weight with regards to the error that has been committed. So if we know the responsibility and we know in which direction we have to move to reduce the error, which is called the gradient. The gradient is simply the most step direction of the weight in which the error is minimized. We can modify the network so that the next time that it sees this particular sample, it will produce less error. Maybe not a 0 error, but it will improve. So it's called, we apply the gradients to move the weight towards a position in which the error will be minimized. So this is very simply how it works. The forward and backward. So essentially, training a neural network is just a bunch of forward and backwards passes. So we give an example, we evaluate the output, we check the error, we modify the network to minimize the error, and then another sample, and another sample, and another sample. And you do this for minutes, hours, days, and sometimes weeks until all the weights of the neural network have converged to a value that minimizes the error, so that when we provide any input, we can expect the output to be quite reliable. Okay, so yeah, there's a certain amount of ways. There's different ways to do this based on how our examples presented to a neural network. So we have, if for example we have, let's say we have 1,000 images, and we have the labels for all of them. So we have 1,000 training images. So one way of doing it is passing in the 1,000 images through the neural network, checking which is the error computed by all of them, and then modify the weights at the same time to minimize that. But that implies having to compute all the samples at the same time, having to store in memory all the activations and all the gradients and all the errors made, and then combining them, and that can be extremely costly if our dataset grows. So the most popular approach, I will skip this one, is actually to doing what is called mini-batch grounded descent, when essentially, instead of processing all the data at the same time, we just pick a subset of it, and we pass the subset through the neural network. We observe which is the outcome of this particular subset. So let's say that we had 1,000 examples, but we're only going to pass 16 at a time because we don't have any more memory. And so we pass the 16 and we modify the weights according to the error caused by the 16 samples, then 16 more images, then update forward, backward, 16, forward, backward, 16, and so on, so on. So this actually works best right now, also because it can be parallelized, because you can have these 16 sample batches and parallelize them in many different ways. But we still have to decide which is the amount of which is the size of samples that we want to use, and this is called the batch size. How many samples will be processed together in a forward and backward pass? So this is the first thing that we have to set up. This is kind of confusing, the naming, I know, and actually in the field it's also kind of confusing. People do not adhere properly to the nomenclature. So if you're reading about this stuff online, be sure to double check because it can be confusing. Okay, so we have this batch size, which is the amount of samples that we pass forward and backwards, and then when we do one forward and backward cycle through one batch, this is called one step. When we have done all training samples once, so we have reached the 1,000 image, 16 by 16, we have eventually done the 1,000 of them, and this is called an epoch. So an epoch is how many times the neural network has seen the whole data set at least once. And then we have this, the number of steps that you need to compute an epoch is essentially this division. So this is a few practical tips. You will see that there are slides that are slightly different. The color is different. So I will stop here to explain some practical aspects of what I'm explaining. Essentially, to define which batch size you should use, there's 4 factors to take into account. First is what's the size of your instance. So what's the size of every particular individual data point. So, for example, if we have one image that is 32 by 32 pixels, this is a small size, so we can use a large batch size with that. But if we have high resolution images, for example, we cannot use a very large batch size because it simply doesn't fit in memory. So another thing is computational efficiency. So if we want to be more efficient, we want to compute larger batches, because the more data we have, the faster it will be able to converge. So this is, you can see already that this is contradictory, so it's a trade-off. There's the stochasticity also, it's a factor to take into account. So the smaller the batch sizes, the more random is the behavior of the neural network, because it's not seeing all the samples at once, it's just seeing a subset of it. So we cannot really predict which are going to be the particular properties of this small subset compared to the general population. So we have this randomness, which a fancy word for randomness is stochasticity. And finally, powers of 2, it's a recommendation for computational purposes. Usually powers of 2 are used. So when you define your batch size, you either use 4, 8, 16, 32, 64, 128, 256, and so on and so on. This is just because of how hardware is computing these things. Yeah, so the other thing that we need to define is how many epochs we want to run this for. So how long we will train for, how many times every sample will be seen by the neural network. So while the batch size is rarely updated, you fix it once, you find one batch size that works for you and stick for it for pretty much most of your experimentation. The number of epochs you have to change constantly. So on one hand, we want the network to converge, to reach a point in which the weights are stable. They are not changing much because the neural network has found a value of weights, a distribution of weights that is comfortable with and doesn't need to update them any further. So if we might want to have enough epochs so that convergence is reached, so that's increasing the number of epochs. Also, we want to have a reliable view into how the neural network is behaving. So if we do very few epochs, we might not have a clear idea of how it is going to behave in the future if we kept training. But on the other side, the footprint of training, which is something that is very important because of the huge electricity cost of training these things, suggests us that we reduce the number of epochs as much as possible, because if we keep doing large experiments with huge amount of epochs, we will be causing a significant harm to the planet. And that's significant harm, like training a model, a very, very big model can be equivalent to the CO2 produced by 20 cars during their lifetime. A paper came out a couple of years ago that compared the CO2 produced by training models and cars and other sources of CO2, and training a very, very large model, sort of model that only Google can, but still was comparable to 20 cars in the US. Okay. So probably the most the specialty of deep learning, sorry for that, is the ability to work with high dimensional inputs. So this essentially means inputs that can be defined by are defined by a lot of variables. So in the case of images, for example, if you have 1,000 by 1,000 pixel images, we have 1 million variables in the input for every sample. And that's a problem. So when we work in high dimensional spaces, in spaces that have a lot of variables, it's very hard to navigate. It's very hard to find solutions for it. So there's a working hypothesis that pretty much enables deep learning. That without this hypothesis, we would have no idea why it works. So we hope that one day it can be proved. It has been tested partially, empirically and theoretically, but it has not been thoroughly proven yet. So the idea is that even though we might have a very high dimensionality in the input, so for example, we have very large images, so we can have a lot of different inputs. If you consider all the possible variations of inputs, all the possible pixel values in a 1,000 by 1,000 image, you can imagine that you can get a huge amount of different samples. Actually, most of them are unrealistic. So if you pick a random pixel value for an image, for all the pixels of an image, you will get with an image that is completely noise and impossible to I mean, it's clear that it's noise and that doesn't represent anything in the real world. So this means that the problem we are working on, which is usually in a particular domain, it's actually smaller in dimensionality than the actual input space. So even though we had an input space that was very complicated, the problem and the solution lay in a simpler location. So this is what is called the manifold, and the manifold is this the limited dimensionality that exists within the input dimensionality. To have an idea of how this neural networks works with these manifolds and embedding spaces, you can imagine here. So we have two types of data. We have the red and the blue, and we have to separate. The neural network task is to separate this data. So if we try to do a linear approach, it will fail because you cannot separate this linearly. So what the neural network does when it has several layers is modifying the representation of the data so that they can be separated linearly. So now this is the same data, but the space has been altered by the transformation of the neural network, by the nonlinear transformation, so that afterwards, after the transformation, now we can separate the blue and the red data with a linear. And this is just another example of doing the same, just doing several transformations in the data so that at some point, if we move it around, stretch it around, and pull it around, we will be able to find a way in this point. Now we can separate it linearly, right? So every layer of the neural network is essentially transforming the space into a simplified version, trying to find this representation that can be linearly separable. Okay, so it's in this kind of manifold space, we are trying to do this gradient descent in which we are going down. You have to imagine going down a mountain, well, a set of mountains, and you're trying to go to the bottom of it. So the bottom is where the error is 0, and the gradient, the direction in which you move, is determined by the measurement of error in every dimension. So one problem we have is we have several dimensions. Moving along several dimensions at different speed is very problematic because it complicates going down. So it's easy to imagine. Imagine you're in the street and you have to go to 5 meters in front of you. So the easiest way is to just walk straight there. But you can imagine that as a 2-dimensional plane. So you could move either in the direction X or in direction Y. So the shortest path is to move at the same rate at both X and Y, so that you are moving in a straight line. But imagine that you're moving twice as fast in one axis, for example, X, with respect to Y. So you would kind of define a parabol to reach the center, to reach the point that you are looking for. And it's more complicated, clearly, than just working a straight line. So it's the same for neural networks. When they are trying to navigate this high-dimensional space, having all these dimensions and moving differently in its dimensions, it just complicates the descent mechanism to minimize the error. Also, it usually finds local minima, which is what you have here. So we're trying to get to the bottom of it, but at some points we have local minima in which it's hard to escape, because to get out of here, you have actually to increase the error. So you have to modify your weights to make more mistakes so that in the future, hopefully, you will find a path to decrease the amount of error. So there are mechanisms to get out of here, but it's complicated. And there are also saddle points. So saddle points, is both of these are saddle points where the curve gets flat. So essentially, at this point, you cannot move in any direction that modifies the error. There's very little gradient. So it's very hard to get out of here, because when you're moving, you are measuring in which direction you should move to minimize the error. The direction is very small, so you get due to very small steps in this direction, and you can get stuck here. Okay, and now I'm going to talk about the learning rate, which is the speed at which we are descending by these curves and mountains. So essentially, you can move in the whole direction of the whole gradient. So you compute which is the error and say, okay, so the direction of this weight to minimize the error is that one. So I'm going to move 1 full unit in that direction. But that it's usually a bad idea. And it's a bad idea because we are using this mini-batch gradient descent. So we are computing the error using only a subset of the data samples. So the actual error when looking at the whole population of samples might be very different. So one data sample might send us one way, for example, this way, and the other data sample might send us this way. So every different batch might be sending us in a different direction. So doing a full step in the direction of the gradient might be counterproductive. It would be better probably if we could kind of find the middle ground, which is called the learning rate. So how much we move in that direction. And the reality is that it's very hard to estimate. The learning rate is one of the main complexities of deep learning today, figuring out which is the best learning rate and how to update it. Because if imagine we have here the loss, and so we're trying to get here to the bottom where the error is minimal. So if we have a very big learning rate, we will be bouncing right and left, so we will never be able to get down to the best scenario, which is where we minimize the error. But if we have a very small learning rate, we are going down this curve in a very small steps, and it will take forever until we reach here. So as always, the best solution is a sweet spot between both. So here you can see an example of how it works. At the beginning of this animation, you will see the error jumps very fast because we have a very large learning rate. So the curve quickly gets into the position, but then steps, the learning rate decreases, and now we're doing very small adaptations, very small modification until we get the actually best possible value. So it's at this point. So in practice, this is the kind of plots that we use for assessing and evaluating deep neural networks. So we have the number of epochs in this axis. This is how many times the network has seen the whole set of data, so 10 times, 20 times. And then in the vertical axis, we usually have either the error or the loss. So here we want to minimize the error. So we are training, we are learning, we are going down the error as we go through epochs, but we are getting stuck somewhere for some reason. So if at this point we reduce the learning rate, we found a jump in the performance, and error is decreased again, and then we get stuck again, and then we can reduce the learning rate again. So with many neural network designs, this is something that happens frequently, that you have to keep updating your learning rate so that you can get smaller and smaller and lower in this error landscape. Okay, so the second practical tips I have for you is about how to tune learning rates. So learning rates and batch size have a direct effect. So you either tune one or the other. So I suggest you figure out which is the batch size for your problem, fix it, and then work on your learning rate. Because if you double one, you have to double the other, and that's just complicating your life. And trust me that training deep learning models is already complicated enough. So you want the learning rate always to be smaller than one, because otherwise it's too big of a step. We usually search it by orders of magnitude. So we test 0.1, we test 0.01, we test 0.001, 0.0001, and so on. You can also do random search instead of grid search. So grid search is just trying them all, and random search is just trying random values. And it has been shown that random search is usually less biased in that regard. But if you have problems or issues, it's in case of doubt, always reduce the learning rate, because a small learning rate will always get you there. It will take a long time, but a very big learning rate might never get you there. So it's better to go small. And when you get stuck in your model, you can always try to reduce it and see if you can improve on top of that. So I will wait here for a second round of questions. See if someone has the hand raised. No. How do you work with binary data? Okay, you don't work with binary data in deep learning. It doesn't make sense. With binary data, you are pretty. It's much better to work with things like a random forest, for example, which are explainable as well. So that's a plus. It's very weird to use binary data in deep learning. Actually, you can if you have a lot of variables. So it's not that. So let's say that you have a black and white image, for example. So if you have a high resolution black and white image, it makes sense to do deep learning, because you have, for every sample, which is an image, you have a lot of variables. So high resolution, so let's say 4K by 4K. And each one of those is binary. That's okay. The neural network doesn't matter, doesn't care if it's binary or a float. Okay, I will move on. So optimizers. So far I have talked about this gradient descent, in which you are going down the slope, but there's several modifications in to stochastic gradient descent, which is the full name of it, for improving the way you find this landscape, you navigate this landscape, and you try to get to these low error areas. So one idea is momentum. Momentum adds the idea that the previous gradient, so the direction you had in the previous step, should be taken into account into the current one. So instead of just going one direction, then the other, and then the other, we just kind of aggregate. So where were we going and in the previous one, and from there we will find the next one. So we are kind of merging the current step and the previous step so that the overall behavior is more smooth and stable, and this makes the convergence easier. It also helps us get out of minimal local minima. We also have a decaying weight parameter that accounts for friction, and in general, it's a very good idea. Then we have a second type of momentum, which is the nested-off momentum, which is essentially very similar, but instead of applying instead of computing the new direction on top of the other, we compute them both at the same time. So it gives a more closed inertia feeling. And then we have variants, several variants. I will not get into too much detail. Ada grad, Ada delta. This is pretty much the most frequent one. The main difference with this is that these methods do compute a learning rate for every single weight differently. So the previous ones, standard stochastic gradient descent, computes a single learning rate and applies it to all the weights. So all the neurons learn at the same pace. This second family of algorithms computes the learning rate for every single neuron, so that every neuron can adapt, can learn at a different pace, and that can, for example, help us when we have this high-dimensional space in which each direction has a different speed. Adam is a very popular approach because it has, it doesn't have it doesn't require a lot of optimization. So if you use it out of the box as it is, it will usually work decently. So it's a very popular approach for prototyping, at least the first solution. Yeah, so in case of doubt, use ADAM by default. It's competitive with minimal tuning. The other alternative that is always there is the standard stochastic gradient descent. So the same old algorithm that was proposed in the 80s is still, with that momentum, is still pretty great. If only you have managed to decay your learning rate appropriately at certain steps, so that it can find the global minima. So we already have defined four hyperparameters that we have to tune when training this thing. So we have to define the batch size, we have to define the number of epochs, we have to define the learning rate, and we might have to define the weight decay to define the weight decay here that implements friction in some cases. So if so we will keep adding. You will see that this list will grow, and this is essentially the main complexity of training neural networks, is that this list of hyperparameters that you have to tune manually, because there are some hints. There's it helps having experience, and there's some that you can automate a bit, but in most cases you will have to find the actual values for this by hand, by experimenting, and this is why training deep learning models is complicated, because you will see this list keeps growing. Okay, so let's talk about activation functions. So we saw that Rosenblatt used the threshold functions that either output 0 or 1. Actually, current neural networks use more complicated activation functions. Instead of only doing 0 or 1, they provide this kind of smooth learning so that you can represent middle grounds of confidence and middle grounds of strength. So this is called the sigmoid, and this is called the hyperbolic tangent. And these two models, two activation functions, were used thoroughly in the last century, but they had several issues that complicated the use of neural networks until 2012, I think, that Relu came along. So for once, there's a zero gradient for most of the functions. So you can see here the slope is 0, and here the slope is 0, and this goes until infinity. So most of the function has 0 gradient, which means that if we are here and we are trying to go down, we cannot, or we can, but at ridiculous speed, because here the gradient is so close to 0 it will take forever. So it means that this will saturate our neuron. And then we have another problem, is that this gradient here, the maximum gradient here, it's actually 0.25 for the sigmoid and 1 for the hyperbolic tangent. So because of how the derivative rule works when doing the backpropagation, we keep multiplying the gradients one after the other to reach previous layers. And if we keep multiplying values that are between 0.25 and 1, what will happen is that we'll end up with a value very, very close to 0. Because, well, yeah, that's how math works. So essentially, this will banish our gradient. And by the time the gradient reaches the early layers, the layers that are closest to the input, we'll have a very small gradient because we will have this multiplied. And these layers won't be able to learn. So this is the vanishing learning problem, the vanishing gradient problem, sorry. And it plagued neural networks for a long time, until the rectified linear unit came around. So this is the ReLU. So we have a linear unit, so it's a linear function, but it's rectified here somehow. So it has a kind of weird angle. It's 0 for most of the function, but then for half of the function, actually. And the other half, it's just equal to the input. So it's a very simple function. It does not saturate because it has a positive gradient for all positive values. It does not vanish because it has always a gradient of 1. So the gradient is constant here. And it's much faster to compute because we have, notice here, we have exponents here. So we have to compute exponents. Here we don't have exponents. It's very easy to compute this, very fast. Problem is what happens if you get here. So if you get here, the neuron is pretty much dead. If for some reason the weight jumps and gets into this region, we cannot get out of here because the gradient is 0. So this neuron will do nothing for the rest of the training. However, this doesn't happen very often. ReLU is actually one of the most safe choices nowadays. And there are also alternatives for mitigating this issue, which pretty much all they do is adding here some kind of minor slope so that you can still get out of here in case of you go negative. But in practice, ReLU is still the most popular approach. So one weird thing is that ReLU is actually linear, right? I mean, it has linear in the name, but we need the nonlinearity for learning nonlinear patterns. And we can see an example of nonlinear patterns in which the linear function fails. So we have these blue dots in the middle and the orange dots around it. And we want to separate them. And the linear function is trying to find a line that now, it's impossible to separate this with a line. On the other hand, the hyperbolic tangent can just find this nice function that separates it, which is cool. And ReLU, what it does, it approximates the nonlinear function through linear functions because it's piecewise linear. So it's the composition of two linear functions. We have a linear function on the left and a linear function on the positive. So we can actually, with enough ReLUs, we can approximate this, and this is why it works. Yeah, this is just another illustration of how. So you can imagine that the space you are navigating, the neural network is trying to find the bottom of a space that has a huge amount of areas like this. This is how ReLU helps represent. Even though it's not completely smooth, it's still kind of linear. It allows you to represent nonlinearities. Okay, I will wait here to see if you have comments or hands raised. I see no hands raised. Okay. So I will go on. You can ask in any language, by the way. I'm just doing it in English because the slides are in English and I'm used in explaining these things in English. But you can ask in Spanish or Catalan. I will answer in those languages as well. So I think I will skip this because it's more boring. Let me go straight. Let me go straight here to the practical tips. Starting with the activation function of ReLUs is pretty much always a good idea. Then you can explore variants of ReLUs or sigmoids in some cases. It's also always a good idea to normalize the data. Okay. essentially, if you do not normalize data, the representation of the space looks like this. And when you normalize the data, the presentation of space looks like this. And this is much easier to navigate for the neural network, clearly. So normalizing is just dividing, subtracting the mean and dividing by the standard deviation, for example. It can be done in several ways. There's still not an agreed way, which is the best. Doing the standard minus mean divided by SDS is the most popular approach. It's always a good idea to normalize your data to simplify the life of your neural network, and also find the proper initialization. So when you start training the network, and you have to assign a value, a random value to every single weight in the network. And this we want this to be small numbers, half positive, half negative. And there are several different ways of initializing them. For when you're using Relus, this is the best approach. If not, there are other alternatives that also work okay. Yeah, some more hyperparameters for our experimentation. We have to decide which activation function we will use. Relu is a very good by default decision. We have to decide what kind of input normalization we will apply. Subtracting mean and dividing by the standard deviation is the most popular approach. And then which weight initialization, which usually is coupled with the activation function that you have defined. Okay, I don't know if I'm going too fast, too slow, or too technical. Hope you're getting the idea. It's hard without seeing your faces, actually. Leave comments in the chat if you want me to take them. So regularization. Okay, this is very important because this is the essence of machine learning. So a lot of people ask me usually what's the difference between deep learning, neural networks, machine learning, artificial intelligence. You have to look at it. Okay, wait a second. Somebody is not muted, and I'm gonna check out who's doing noises. Miguel Ángel Rojas Gómez. Miguel Ángel, please, could you mute your mic? Thank you. Okay. So why do we need regularization? Yeah, I was talking about what's deep learning. So you can visualize it as a tree. So artificial intelligence is pretty much the general term to refer to everything. And then within artificial intelligence, we have machine learning, which is essentially learning from data. So learning from different ways of learning from data. You can either have the knowledge coded somehow or learn from data, and that's machine learning. And then within machine learning, you have artificial neural networks. So you can learn from data using a model that is composed by neurons, which is an artificial neural network. And then within artificial neural networks, you have those neural networks that have a lot of layers, usually by a lot of layers. I mean, anything above 5 is probably considered deep learning, but it's very fuzzy. I mean, nobody has a proper definition for it because before the explosion of deep learning, neural networks were around, but neural networks with more than 3 layers were very weird because we could not train them because of the problems we had, but now we can train them. So you have this categorization from the most abstract artificial intelligence, machine learning, artificial neural networks, and deep learning. So anything below machine learning is trying to generalize, is trying to learn from data so that what it learns can be applied to different data that it has never seen before. And that's very important because that's the difference between machine learning and optimization. If you just have data and want to solve that data, it's an optimization problem, and you're done. When you look at the data, you learn from it, and you're done. In machine learning, you are trying to generalize. So you look at some data, you try to learn from it, and then you hope that it will work on other data that the model has never seen. So this is when you put it in practice and you put it in action. And that's what generalization means. It means I'm learning on some data, and I hope that this will generalize, that this model will also behave as I expect when I feed data it has never seen before. So the problem is we have to learn patterns from the data, but those patterns that will be also found on that data that will see later that we will not be able to train on. So we have to find these good patterns, which is, as you can imagine, very difficult because it's for the neural network. We are using an optimization algorithm going down the slope, so that doesn't understand of good and bad patterns. It just understands of going down. And going down, you cannot control. If you're going to focus on things that will later be useful, for example, which is the color of the tail, or things that are not useful, which is, for example, which is the color of someone's clothes, which might not be relevant for the task, but for some reason it's there. So it's a pattern that the neural network might learn. And yeah, they will always go for the easy patterns essentially because they are going down the slope. And going down the slope, they will just go in the direction in which it goes faster. So we have to be careful. Generalization is sweet spot is really complicated to get there. You eventually get there to a certain degree, so you will never get the same performance in training data and then on data outside of the distribution. So for training neural networks, I think it's also good to understand the concept of underfit and overfit. So essentially, when you are training a neural network, it has the capacity to learn these patterns in the data that will eventually allow it to work perfectly on the training data. But it might be the case that if you work perfectly on the training data, it will work terribly on any other data. So we want to find a middle ground, somewhere where we are finding this. We are performing decently on the training data, and we are also performing decently on data we have never seen before. So when we are performing too well on the training data and failing on any other data, it's called overfit. So we are learning too much from the training data. We're learning the wrong things from the training data, and then these things are not repeated or found in other samples. So this is bad because we think that the model is going to behave very well, and then when we put it in practice, we see that it's terrible. On the other hand, we have underfit. It's that we didn't learn enough from the training data. So we are not good enough at solving the training problem. So we have to be somewhere in the middle. And for understanding that, so let's see an example how it works. We have blue dots and red dots, and we are trying to find a function that separates them. So we have one solution that kind of works, which is this function, a parable here, kind of separates. It makes some mistakes. These reds shouldn't be here, but that's okay. I mean, it's very few errors. We can live with that. If we do that, then we are doing overfitting. So if we try to train too much and learn too much from the data, we will end up with a function that fits the data. But for example, if we add one blue dot here, which makes perfect sense, it will be categorized as red, which is a mistake. So this is a problem. And this is why overfitting fails. And this is even a more problematic case of overfitting, more extreme case of overfitting, because blue dots in any of these areas would still be classified as red, which would be mistakes. So for handling overfitting and underfitting, we have to consider three main aspects. One is model capacity. How complex is your model? How many trainable parameters it has? How many weights it has? How many and that's essentially the complexity of the network. The more complex the network is, the more weights it has, the easier it has overfitting because it has a more expressive power. So we might want to limit the number of weights and the number of neurons, because if we add too many layers, too many neurons, we will end up with a model that can mimic our data very, very well and then fail in anything else. Also, the amount of data that we have. So the more samples we have, the harder it is to overfit, because you can imagine if we had a lot of samples here, if we had more samples here, more blue samples here, this overfitting would not have happened. If we had a blue sample here and a blue sample here for training, then the overfitting would be harder, and we would get a much better function. So the more data you have, the better. And this is why always in deep learning we say that the more data, the better. Don't ask me how much data I need. Give me all the data you have. Yeah, that's the number one question that you get when you work in deep learning and you try to apply it to a problem. That people come to you and say, okay, how much data you want? No, that's the wrong question. The question is how much data you have, because I need all of it. And regularizers are methodologies that try to prevent this from happening. Okay, so now we will see a few regularizers that are methods that try to avoid the overfitting. So this is a slide I like to put for sanity reasons. I mean, pretty much everyone working on artificial intelligence, data science, or anything related should be aware of it, of the importance of separating your data into a train, test, and validation set, because otherwise you cannot trust your results. And if you cannot trust your results, you're pretty much doing, I don't know, you're not doing science. I don't know what you're doing, but it's not science. So essentially, we have the training set, that is the data that we use the model, that the model will be able to see and learn from. So this is the data that the model will use to define how it modifies itself. And we need it to be as large as possible. Overfitting to this data is inevitable. Even desirable at some point, and we should be able to overfit to it to demonstrate that the network can in fact memorize patterns in the data. And then we have, in deep neural networks, we have this validation set, which is a part of the data that is not seen by the neural network for learning, but it's only seen by you for tuning the hyperparameters. So essentially, when you're trying to define this list of long list of hyperparameters that we had, you will want some indication of what's the effect of altering one value or the other. And for that, you use the validation set. So you check the performance in the validation set, and you see if increasing the learning rate improves or not. And then based on that, you decide to increase the learning rate or not. Overfitting, funny enough, overfitting is still possible in the validation set, even though the weights of the neural network are never modified according to it. You can still overfit to it because of your decisions, because you have to make so many decisions in hyperparameter tuning that eventually the neural network design will be partly adapted to the validation set and might not work as well on the test set. And this is the last one, the test set. The test set, it's difficult to make people understand how to properly use the test set, because you can only use the test set once. If you use the test set more than once, then it's not a test set anymore. Test set is used to have a clear and independent and reliable idea of how your model behaves. And this can only be done if you do not make any decisions based on it. So the moment you test it, you get the result, and that's it. You report it. You give it to the client. You publish it in a paper. That's it. You run it once, and you are done. If you modify the neural network according to the test set, you are not having a test set. You are having a validation set. And that's very important, because otherwise we cannot trust the results. This is the most reliable indication of how your model will perform in a real-life world scenario. And if you don't have this, you have no idea of how your model will perform once it's deployed. So this gives us the fifth practical tip slide, which is things that you should never, ever, ever do. First is mixed data, which is correlated in the different splits. So for understanding that, consider an example of a medical case in which you have, for example, radiographies of different patients. So let's assume that some person has more than one radiography because they did some follow-up image taking. So you should never have images from the same patient in different splits. If you have a single patient, the single patient goes either to train, to the validation, or test, because otherwise there's some correlation. If we split the radiographies and put one radiography of the patient here, another one here, then there's a relation between these two data sets. And something that was learned here can be reused here, even though it shouldn't. So let's say, for example, that this patient had a watch in his or her hand, and the neural network, for some reason, learns that the watch is important to determining if this person is sick or not, which it should not do that, but it might do that because it's a pattern that it has for some reason. For some reason, people who is sick in this data set use more watches than people who are not sick. So it might learn this bad pattern. And then if we have these samples of the same person here, the same person with the clock, with the watch, will also be here, and our test set will say that it works fine. On the other hand, if we have all the samples of the same person here, we have no idea if the people who are sick will have watches in this test set. So hopefully they won't. And when we test this here, we will see that it fails, because it will try to look for watches, it won't find them, and the neural network will perform poorly. So that's an example of why you don't want to keep correlated data in the different data splits. Yeah, some other tips. Reproducibility is a very big issue in deep learning because obtaining the same results twice with a model which depends on so many data in so many parameters that are randomly initialized is very complicated. So you always want to make a strong effort on reproducibility, on fixing a numerical seed so that every time that you start randomly, you are actually starting the same way randomly and with the same random numbers so that you can get the same results again. And most importantly, so that other people can test what you have done and they can reproduce what you have done, because essentially a single person running a model and saying it works, it's unreliable. So you should never believe that the trained results are going to generalize. So don't expect a model that performs very well in the train set to perform magically well when applied in practice if you haven't thoroughly evaluated it with a validation and a test set. And also never assume that the data set is free of bias. So bias is these patterns that will try to fool the neural network, that the neural network will try to learn from, and make everything bad because they are unrelated with the problem, unrelated with what you want the solution to be. Yeah, and finally, the balanced data set. So usually when you are learning some problems, it's very hard to have a homogeneous amount of samples for the different classes or for the different types of data. So for example, cats and dogs, so you have the same number of samples of cats and dogs, or you're estimating the price of houses, having the same number of data samples for all house ranges is hard. So balanced data sets have a big impact on learning as well, and you cannot assume it, and you have to make sure that that you are correcting for it. And I'm gonna pause again here and see if there are any hands raised. Okay, so somebody asked, is deep learning often used for training data other than images, or are images the primary reason to use deep learning? Yeah, Kat, you should raise your hand. But since you have written it already, I will answer. For the rest of you, please raise your hand so you can speak for yourself. Deep learning is pretty much for any data that is high dimensional. So it means a lot of samples, and every sample is very complicated. If you have few samples, deep learning is hardly a good solution. And if your samples are very simple, deep learning is definitely not a good solution. If you have large number of samples with a large definition for each one of them, then deep learning is a potential candidate. The thing with images and deep learning is that the models that we define for images, which are called convolutional neural networks, that maybe I will give another lecture another day on that, work very well. It's the best model we have found. So we have defined, in deep learning, we have defined models for sequences, we have defined models for arbitrary data, and pretty much CNNs, convolutional neural networks for images, are the best we have among them. So images is the most well-solved problem in deep learning today. And we are working hard on other kinds of problems in graphs. For example, it's very complicated dealing with graphs, but there's also some nice models for that. But CNNs are the most mature, and they are the closest to application, I would say. So that's why they are so popular and why people always use them as an example. Okay. No more, I can see no hands raised, so I will go on. Okay, we have half an hour left. I don't know how we are on time, but let's try to cover as much as we can. Okay, so this is my particular recommendation on how to tackle a deep learning training project. So essentially, I usually recommend 3 steps when you are training a deep network. First is to manage the network to learn something, anything. Please learn. You will often find yourself trying to train these things, and for some reason it doesn't, and you check it with the. So essentially, you have to compute which is a random behavior. So if you had a random network or a person randomly trying to figure out which is the task, how good would it do it? So it was just flipping a coin. and then try to get a network that works better than that. So if you manage to get a network that is better than flipping a coin, then you have something that has trained anything. At that point, you know that the architecture you have and the setting that you have is close to something that can find a solution to the problem. It gives you a rough estimate of the hyperparameters that you should be using. Then the second step, once you have managed to overcome the random performance, is to try to learn everything. Try to overfit. See if the network has the capacity enough to learn complex patterns in the data, even though if those patterns are not the ones you want. So even though this doesn't generalize, even though it works horribly in the validation set, you keep going and try to get a very good performance on the train set, because that will give you an idea of which is actually the topology of the network that you need for the problem. It might be too large, because when you overfit it, usually you are using a network that could be reduced, but at least you know which is the ceiling, and from there you can reduce. And once you have reached overfit, then we get to the third step, which is just learning the right thing. It's getting good performance on the validation set. Notice here we are just working on the train set. We are not looking at the validation set. Just learn something in the train set, learn everything in the train set, and once you have found the network that you can overfit to the train set, then try to get it to work in the validation set, which it shouldn't. Probably out of the box, it will fail at some point. And then you will start doing some regularization things and modifying and reducing the complexity and so on until you finally get it to get a good performance with the validation set. And once you're happy with the validation set performance, you close it, you stop it, and you report your results on the test set, and you're done. Okay, so regularization. I will review a few techniques, a few regularization techniques. I might not go over all of them because some of them are a bit technical, and there's a lot of them. I mean, there's a lot of them. People dedicate a lot of time to this kind of thing because it's very important. Manage to get the network to avoid overfitting. You can imagine how important it is. So the most popular, the ones you should always do because they have no downsides. So this only it's very good to use them. I mean, they have no side effects. Is early stopping and data augmentation. So early stopping is well for a regularization technique is quite simple. It's just defining a policy by which you stop training. So how many, I will not train for 80 epochs. I will stop training when I'm unable to reduce the error I make for 2 consecutive epochs, for example. So stop training at some point, given some policy, so that your network doesn't reach a state in which it's overfitting and it's fooling you, to say it. Yeah, and it also helps with footprint because we don't need we don't need 40 epochs of overfitting to know that it's overfitting. So using an early stopping policy is always a good idea. And then we have data augmentation. So as I said before, data is a key aspect in deep learning. We need a lot of samples because the more samples we have, the less overfitting we will have. And data augmentation is a mechanism to get more data for free. So it's essentially slightly altering your samples so that they look like different samples, but they are actually the same. Again, for example, of images, you can do that just by, for example, moving the image a bit to the right, or moving it a bit to the left, or rotating it 5 degrees clockwise, or rotating it 5 degrees counterclockwise, or by applying a vertical mirror on the image, or by applying a horizontal mirror on the image. There are many ways in you can modify the image and still represent a valid sample. And you should do it as much as you can because all these alterations will eliminate all these bad patterns, all these useless patterns that appear in the data and that are not useful for us. But you have to do it with care because the data augmentation that you can do depends on the problem and the data at hand. So you have to think this every time. For example, doing this mirror that I was saying, you can imagine a vertical mirror and a horizontal mirror of the image. So if you are doing some kind of text processing, doing a vertical mirror is a very bad idea because the text becomes completely different. Letters become different. The text becomes unrecognizable. So you have to consider how will each data augmentation method alter your data. Doing the vertical flip, for example, is difficult in most cases because orientation in our human world, orientation is usually important. So you don't want to have grass in the sky and sky on the ground. So yeah, you have to think this carefully. But again, regularization is always, this is something that I try to repeat very frequently. Regularization should only be applied at this step. So at this point, you are trying to overfit. So applying regularization in steps 1 or 2 doesn't make much sense. Okay, and another practical tip is how we assess the performance of deep neural networks, how we make our decisions on training. So usually we look at these curves. As I said before, this is the epochs, the number of times we have processed the whole data set through the neural network. And then we can have either the accuracy, which is a curve that goes out. So the higher the better, because we are learning. Or we can have, sometimes we have the loss. In this case, it's the other kind of curve. You know, it was, we had a slide before that we had the losses curves here. So this is the same kind of function, but epochs is also in this x-axis. But here, instead of accuracy or whatever metric you're using, we are measuring the error. So we essentially work with these two plots, the loss and the performance plot. So we launch a training and we see how it behaves. We have the training and the validation set. And we see that the training is doing fine. And then at some point, training keeps doing fine and the validation set gets stuck, right? So it means that good patterns were learned. And at some point, learning good patterns became too hard. And so bad patterns become easier to learn. And at that point, the network started focused on learning these bad patterns and improving them and optimizing them and getting better and better in the training set, but then failing, well, not failing, but staying the same at the validation set or even decreasing a bit the performance. So, for example, if I had to choose a model in this, you can see this, every point in this function is a different model, is a different step in the history of the neural network. So if I had to choose one of these for applying in performance, I would probably choose this one. So this one at epoch 41 has a relatively small gap between the training and the validation, and it's close to the maximum of the validation curve. But any model, this also would be a good candidate, and even this, yeah, probably this is also a good one. Validation and training are very, very close together, so there's very little overfit. So usually this is the kind of curve you will see. You will see the train that goes up and the test. Well, this should be validation that eventually it will get flat and start getting worse and worse as overfitting gets implemented. This is why you want to use early stopping to stop the training here, because we don't need to keep seeing the rest of the curve as this goes worse and worse. And there are some cases, some really weird cases. So sometimes you have things like this. Where it's the train is learning from the start and the test is failing from the start. So there's here the problem is that from the very beginning there's overfitting, so there's almost no time to learn from the data. And looking at these curves is like it's funny, but it's complicated. It's like trying to understand why somebody is sick without being able to look at them or touch them. It's from the distance. So here we have another model in which the network is hardly improving the random behavior. I think this was a binary classification problem, so random behavior 0.5 accuracy. And the model is stuck here. It cannot learn. It gets it's stuck in the random behavior. At some point it starts learning. It found some patterns, some bad patterns in the data that allows it to obtain better results in the training, optimize it. But unfortunately, these are not found in the validation set. So this is a bad model. So here are some tips on how to operate with curves and how to interpret them. So if you see no trend or everything is so chaotic, you probably want to simplify the problem of the model, decrease the learning rate. Also, having a very large learning rate helps. provides this noise. If you decrease the learning rate, you will get a smoother curve. You have to check if you have wrong data, if your pre-processing is right, and your weight initialization is right, because this is what's needed to get to step 1 of training, which is get better than random. Sometimes you see a loss explosion and the error skyrockets for some reasons. It might be because there are some corrupt data instances, or at some point the gradients exploded, and then you have to check the weights of the network to see if there's something weird going on. And sometimes the loss goes down and the accuracy goes up. So usually what you see, we have the accuracy curve and the loss curve, and this will be kind of symmetric, right? Because the higher is the accuracy, usually the lower is the loss, the lower is the error that we are making. So this should be kind of symmetrical. It's always good to look at both of them, just in case, but pretty much they tell the same story. But sometimes you see something that doesn't make sense, which is that both go in the same direction, both grow and both decrease. And this is because of the neural network works in a probabilistic way. So the error is computed probabilistically, but the accuracy is not. So to make this simple, consider you're trying to classify between cats and dogs, and you have this sample of a cat in which you are 51% certain that it's a cat. So according to the accuracy, this sample, which you have classified as a cat because you are 51% confident, is a hit. You're right. You made it. It's a cat. Correct. Great. But according to the loss, you made an error of 0.49. So it's a huge loss. It's a huge amount of error. There's room for improvement. So sometimes you will see that the curves in accuracy stay the same because you haven't reached the break point in which you change the prediction, but the loss is altering because of these probabilities, because you are modifying and getting closer to the actual threshold in which you stop one prediction and predict the other one. Okay, I'm gonna stop again here. Check for raising hands. No raising hands. And no chat questions either. No wonder. Okay, so I have 10 minutes left or so. So let me check which parts I think are more interesting to. Oh yeah, we're close to the end, so I think we can do it with the time we have left. So there are all regularization which are a bit more complicated. Some of them try to control the value of the weights, because usually when the weights go to extreme, go to very high values, it means that they have become too specialized, and specialization in this sense is usually related with overfitting. So usually weights are some kind of controlled. I will not get into detail on that. There's another popular approach, which is the batch normalization, which does the same, but well, something similar, but with activations. So the weight, remember, the weight is the strength of the connection between two neurons, and the activation is the actual output of the neuron. So you can also normalize the activations, the outputs of a set of neurons, so that these values will also get within a controlled range of values. And this also helps in many ways. The actual mathematical reasons why this works, it's not so clear. This is one of the issues with deep learning, is that it's extremely complicated to demonstrate anything mathematically. So pretty much all advances are made empirically, and doing things empirically in a domain where you have so many hyperparameters and so many dependencies and variables and so on, it's very complicated. So it's why deep learning is usually an unreliable field in the terms that you cannot really expect that something that someone said or published or did will work for you. Because we just don't know. There's so many different reasons why it couldn't work. That it's unlikely that it will. It's that's why we need to make an effort in reproducibility and explainability. So there are many ways in which you can normalize the data, as you can imagine. I will explain this one because I think it's a cool one that gives a good idea of how this works. So we have a standard neural network. This is the first layer. So here comes the data. Every neuron receives all the data. Then we have the second layer with every neuron connected with every neuron of the previous layer. So we have 2 hidden layers and then the output. So here we have the classification. So our flow of data will be like this. We'll make the prediction and backpropagate and so on. So the dropout methodology, which is a regularization technique, essentially what it does, it cuts out some connections randomly during training. So every time you are doing a step, every time you're doing a forward and backward step, you randomly disconnect some neurons, given a probability, usually which is between 0.2 and 0.5. So it means that every time that you see that you do a step, the topology of the network will be slightly different, and the neurons available will be slightly different. So co-adaptation will be much harder. It will be very difficult for neurons to learn that they depend too much on previous neurons because maybe in the follow-up step they are not connected to this one. So dropout works very well for regularization. It decreases overfitting, it delays overfitting significantly, and you can get better performance in the validation and the test set. But it also slows down the training a lot because essentially this lack of co-adaptation makes it very hard to converge. And every time you're doing a forward and backward, you have a different network, you're training a different network, and it kind of getting the whole thing to converge takes a lot of time. So that's not good. Also, it adds another hyperparameter that we have to tune, and it affects so many others. Usually, also, yeah, I didn't get into convolutions, which is the topic on images, but usually for fully connected layers, it works very well. For other architectures of neural networks, it might not work that well. Okay. So also I want to finish with a recommendation of how to set up experiments in deep learning, because this is something I also found that people that are getting into the field could benefit from. So first is doing one experiment at a time. I mean, it's already complicated enough to do more than one experiment. So just stick to one experiment, get your conclusions, and then tackle a new one. And first, you need to properly analyze where you are. So what is wrong at the moment? What can be improved? What part of the problem you want to tackle? You want to be able to underfit. You want to be able to overfit. You want to be able to fit perfectly. How can we achieve that? How can we modify the neural network? Which hyperparameters we can tune? How can we change the architecture to reach that goal? So you have to have a clear idea of which are the tools that you have and which are the problems that you have, so that you can match one-to-one. So once you have decided what has to be fixed or improved and how can it be done, then you have to decide which is of the many alternatives, because usually you don't have just one alternative. You have like 10 regularization methods and 10 ways of reducing the complexity and 10 ways of increasing the depth. And so which alternative is going to work better? It's better to test several of them because so little is known about them, so we cannot rely too much on what one particular people said. So if notice I never said always use this or always use that, because this is rarely the case in deep learning. You always have to find which is the optimal solution for your particular problem. And finally, an ablation study is very important. So ablation study essentially means, so I'm adding 3 functionalities, A, B, and C. And I test the model with A, B, and C, let's say, for example, using ReLUs and using stochastic design and using Dropout. And I get a performance of X. So how do I know which is the impact of every of those components separately? If I don't know which contribution of these the different things that I'm doing on the network, I cannot know which one I should be using. So an ablation study is simply put running experiments using only one alteration at a time. So I'm adding Dropout alone and test with it, see how it behaves. Then I change the activation functions to relu and see how they do. And then I combine both, and I do activation function with relus and dropout and see how they do. So I can know the impact of they separately and they combined. And by knowing the performance separately and combined, I have a whole idea of what's the impact of these methodologies on the model. And that's the best way we can do when you are working empirically. And finally, some tips when you are underfitting: check the initialization, the learning rate, the batch size, increase the complexity, and when you're overfitting, just apply regularization and try to reduce the complexity. And finally, maybe this shouldn't be so late in the slide deck, but well, it's a lot of stuff. It's difficult to put in order. We have to define what we are trying to learn. So essentially, how we compute the loss, how we compute the error, because we have this data that has a label. In the case that we are working a supervised problem, again, there's also approaches to work with unsupervised learning in deep learning, but I think it's too much for this session. So, for example, if we are trying to classify things into n buckets, let's say, we will use a softmax function, which is this one that turns values into probabilities. It's a nice curvy thing, plus a cross entropy with n neurons to compute the error. If we are doing a regression problem, for example, trying to estimate which is the price of houses in a certain town, so you have numbers. So the output prediction is a number of how tall will somebody be, or which score will somebody get. Anything that is numeric is a regression problem. You will use a different error measure, for example, a mean square error. But in essence, there are as many error functions as problems. So you should also take a deep look at that to make sure that you are trying to learn what you want to learn. And more hyperparameters to tune. We have the network capacity, which is how many layers we have, how many neurons per layer we have, when we stop training, how we modify the data in the input, how we normalize the layers by, well, I didn't got, this is the part that I didn't got to explain, but there's also ways in which you can normalize the data and has hyperparameters and which loss function you use. Okay, so I will stop here. Because I think it's a lot of stuff. I know it's dense, but I think it's the amount of depth is appropriate for pretty much everyone. So let's see. We have a couple of questions in the chat about the data augmentation. What happens with the images annotation? Labeling data for a classification task might be easy, but what happens when the labels are bounding boxes or the data set is of images that have been segmented semantically? Is there a straightforward way to transfer the annotation from the training set to the augmented data? Okay, so when we are working with segmented images, essentially what we have is a pixel-wise classification problem. So you have an image and you have the contour, the silhouette of a cat or a bicycle or a house or a tree, and you have to consider that actually the goal of this task is to predict the classification value of every pixel. So we want to discover which pixels belong to a cat, which pixels belong to a house. So essentially, the problem becomes a problem of pixel classification. It's kind of hard, as you can imagine, because there's a lot of pixels and classifying them correctly is complicated, but there's a lot of models that already solve that very competitively. And somebody else is asking, naive question for a basic deep learning course. Even if, as you said, deep learning is an unreliable field, for a particular deep learning system, if we know so well how it was trained, might this allow some kind of explainable AI? Okay, so explainable AI is wrong. It's wrong. It's a wrong word. Because explainable, it means that it can generate arguments, and we are way far away from that. I mean, the closest we are is to inspectable AI in the terms of deep learning. In deep learning, everything we can do is try to understand why how the model reacted to some parts of the data. So, for example, which kind of visual inputs generate which kind of response. But that's hardly an explanation. That's just an interpretation of how it works internally. And it's very complicated because since everything internally in a neural network is just a multiplication of weights and activations up and down, matrices, gradients, and so on, we don't have, the neural network has no internal representation of what concepts mean, and it has no semantics whatsoever. So be very careful of whenever people talks about semantics or explainable in the terms of deep learning, because it's a very, very emergent field, which is just in its infancy. So all we can do is try to understand how the neural network will react in certain domains. For example, by blocking, let's say we are processing images, so we will pass images which has a black patch on top of that, because we want to see what happens. So we have images of cats and dogs, and I will put a black patch on top of the cat and see if the neural network will predict the cat anyway. I mean, can the neural network predict that the image is a cat even if the cat is blocked out? If so, it's bad news, because it means the model is looking at other things and not the cat itself. So things like this is what we currently do to try to understand if a neural network has learned what we want it to learn, because knowing the difference between good and bad patterns is very hard. And yeah, I think that's enough. Thank you.
Thank you very much, Dario. It was a very good session. I only want to share with all the attendants that in the next following days you will receive a short survey to help us to improve the further the sessions. Sorry. Now I'm back. Hello?
Your connection seems to be unstable.
Yes.
Okay. Yes, well. Now I'm here. You will receive the survey and the video of all the session if you want to review some part that you have more interested about it. So thank you very much again, Dario, for all this masterclass, and see you in the next following masterclasses from CDI.
Thank you for inviting me.